this video, we'll discuss the analysis of optical multilayers like this, where you have a number of layers with parallel interfaces that are made of different materials with different indices of refraction or perhaps different magnetic permeabilities. And we're interested in the intensity of the transmitted beam and its polarization given the intensity and polarization of the incident beam. So in this problem, we have a series of regions with different properties, and the task boils down to applying the boundary conditions between these regions for the tangential components of the electric and magnetic fields. The whole analysis should be performed at the fixed value of k parallel. That's the projection of the wave vector onto the plane of the interfaces, because it is the same for all waves that are being matched. Thus, in each region, we introduce two plane waves with the same values of k parallel, but values of kz that differ in sign. By convention, we'll assume that the real part of kz is positive, or if it's purely imaginary, then its imaginary part is positive, so the wave corresponds to the evanescent wave decaying to the right. Now, the arbitrary polarization of the incident beam can be represented as a superposition of two beams, one with electric field normal to the incidence plane and the other with electric field parallel to the plane of incidence. Due to the superposition principle, we can consider these two components of the beam separately and then add them together. So the problem splits in two parts, one for determining the propagation of the beam with perpendicular orientation of the field, and the other, the one with parallel. The methods for the solution are entirely analogous, so let's pick one polarization and stick to it. So I'm going to use the one with E perpendicular to the plane of incidence. And then the expressions for the E fields in each region simplify, and I only have two E field amplitudes in the y direction in each region. It is convenient to introduce different phase conventions for different regions. So if we set the origin to 0 at the first interface, we'll keep the definitions for the waves in regions 0 and 1 unchanged. So we'll have just e to the I kz in the exponent. But in the following regions, we'll use a different convention. So let's introduce the coordinates of the interfaces as z2, z3, and so forth. So those will be given by the sums of the thicknesses up to the given layer. And in the layer number n, except for 0 and 1, we'll introduce the amplitudes in the following way. So in region number 2, we'll have E2 plus e to the I kz2 with the origin of z shifted to z2. So we'll have two waves like this, plus and minus kz2, z minus z2. So the advantage of this choice is that when we do the matching at the given interface, so for example, this interface between layers 1 and 2, the phase factor for the region on the right will be just 1. So the expressions for the matching of the wave amplitudes will simplify. With these definitions, let's write the boundary conditions for interface between layers 0 and 1, and then layers 1 and 2. So adapting the discussion from the previous lecture where we just considered one interface, the matching condition at interface between 0 and 1 will look exactly the same as in the derivation of the Fresnel equations, with the exception that now we have the left-going wave in region number 1. It was not present in the previous discussion because we just assumed there is no beam incident from the right. But here we have multiple interfaces, so due to multiple scatterings, there will be generally a left propagating beam. So the boundary conditions at the interface between 0 and 1 will look as follows. So we match the tangential component of the electric field. That will give us E naught plus E naught minus equals E1 plus E1 minus. The E1 minus is the new piece that was absent when there was just one interface and only right propagating beam on the left. The second condition from matching the tangential component of H will be 1 over mu k z naught E naught plus minus E naught minus equals 1 over mu 1 k z 1 E 1 plus minus E1 minus. And everywhere the kz is determined from the condition that k parallel squared plus kz in any layer, let's put it in squared, equals kn squared, where kn is just n in layer n omega over c. Here n sub n is the index of refraction. Let's now write the boundary condition for the second interface. There will be one important difference, and the difference comes from the fact that the phases in region number 1 are defined with respect to the left boundary of that region. So the amplitudes of the fields at the interface with region number 2 are shifted by the phase kz1d or minus kz1d. So explicitly, writing this down, the field on the left will look like E1 plus e to the I kz1d plus E1 minus e to the minus I kz1d. And to the right of the interface, it's just E2 plus E2 minus because of our choice of the phases that vanish at this boundary. So compared to interface between 0 and 1, now we have to carry these phase shifts. Same thing for the matching of the magnetic fields. So we're going to have 1 over mu1 kz1 E1 plus e to the I kz1d minus E1 minus e to the minus I kz1d equals 1 over mu2 kz2 E2 plus minus E2 minus. Then we can keep going like this for each subsequent interface, and the boundary conditions will look pretty much exactly like in this case, except that all the indices will be shifted by 1. One thing I forgot is to include the index for D because the thicknesses of our layers are generally different. So now we see that each interface, or rather each region that we add to the optical system, adds 2 unknowns. Those are the 2 field amplitudes, but it also adds 2 extra boundary conditions. So we have exactly the right number of equations to determine all the amplitudes if we know any 2 amplitudes. So normally, if we have a beam that's incident on one side of the system, we know the amplitude of the field in that beam, and we know that the amplitude for the beam incident from the other side of the whole system is 0. Those two amplitudes are enough to find all the other amplitudes in the system. We just need to solve a bunch of linear equations. This approach is straightforward, but not particularly elegant or convenient. When the number of interfaces is large, there's a whole lot of equations that need to be solved, and it's clear that some kind of systematic handling of these equations would be beneficial. In order to do this, there is a very useful approach that is called the transfer matrix method. It can be used in multiple problems, not necessarily for optical multilayer. It's also quite useful in quantum mechanical descriptions of multilayered systems. So we will now turn to the discussion of this method. Let's focus on the boundary condition for one of the interfaces, which connects the field amplitudes to the left and right of that interface. There are two equations and 4 field amplitudes, so that we can express any 2 amplitudes through the other 2. So in the transfer matrix method, we need to express the 2 amplitudes to the right of the interface in terms of the 2 amplitudes to the left of it. We introduce a matrix, let's call it T 1 to 2, that when multiplied by the column vector E1 plus E1 minus will give us the column vector E2 plus E2 minus. This matrix is called the transfer matrix because in a way it transfers the 2 amplitudes from one layer to the amplitudes of in the other layer. We can write a similar connection at any interface. So this was for the interface between the first and second layer, but we can then write E3 plus E3 minus equals T 2 to 3 with the amplitudes in the second layer. Now the convenient thing about these matrices is that you can combine them by simply multiplying the 2 matrices, or more than 2 matrices. So indeed, if I want E3 plus E3 minus, I can write this as T 3 to 2, and then substitute the column vector that we can find from the first equation. So if I insert the right-hand side from that equation, I'll have T 1 to 2, E1 plus E1 minus. So this is now the transfer matrix 1 to 3. And I can obtain it by simply multiplying the 2 matrices for the intermediate connections. This is the basic idea of the transfer matrix method. We can find the transfer matrix for each interface, and they should all look pretty much the same, because all the expressions, all the matching conditions look the same. It's just the indices are different. And once we know the transfer matrix for each interface, I can simply multiply them together, and that will give me the transfer matrix for the whole optical multilayer. I will get the 2 amplitudes to the right of the multilayer expressed linearly through the 2 amplitudes to the left of it. So that way I can find the amplitudes in layer N, which is the rightmost layer, by multiplying all the transfer matrices for the interfaces that are present in the system. And the resulting product of the matrices can just be called the transfer matrix of the multilayer. Suppose now that we have computed the transfer matrix of the multilayer. So it gives us the amplitudes to the right of the multilayer. Let's call it ER plus and ER minus instead of EN. And then here's a transfer matrix with elements T plus plus, t plus minus, t minus plus, t minus minus, and here we have E left right going, E left left going. So once we know this matrix, we can easily calculate the transmission and reflection amplitudes. For example, for a beam incident from the left, we have the amplitude ER minus equals 0. There is no beam incident from the right. This results in the equation from the second line of the matrix equation. 0 equals T minus plus EL plus T minus minus EL minus. This immediately gives us the reflection amplitude. We find that EL minus, which is the reflected amplitude, divided by the EL plus, which is the incident amplitude, is simply equal to minus T minus plus divided by T minus minus. Now the transmission coefficient is given by the ratio of ER plus to EL plus. Now from the first component of the matrix equation, we have ER plus equals T plus plus EL plus plus T plus minus EL minus. We can divide this equation by EL plus. That will give us this ratio that we want on the left, this one. And then the right-hand side is T plus 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 T plus minus. And then we have the ratio of the reflected amplitude to the incident amplitude. And we already know this ratio. So if we substitute the right-hand side here, we have minus T minus plus divided by T minus minus. Overall, we can combine the two terms. That gives us T plus plus, T minus minus, minus the product of the off-diagonal terms, divided by T minus minus. And the numerator here is just the determinant of the transfer matrix. So we can write it as determinant of T divided by T minus minus. So this gives us the transmission coefficient. If we want the transmission and reflection coefficients for a beam that is incident from the right, we can simply invert the transfer matrix and do the same thing as we did here. Let's now come back to our boundary conditions and make one last touch to make the transfer matrix method even more convenient. So here are the boundary conditions we used for different interfaces. The equations for the first interface and all the other interfaces are slightly different. There are factors involving the phases with the layer thicknesses D at all the interfaces except for the first one. And the first one does not include this. This is due to the choice of the phase convention that we used. Now, we can separate the propagation of the waves through the bulk of the layers from the transfer of the amplitudes across the interfaces. This makes the equations somewhat more transparent. So here's what we can do. So far, for each layer, number I, we have introduced the field amplitudes in the following way. We had a right-going amplitude, E sub I plus, that came with a phase factor e to the I k zi, z minus zi, where zi is the coordinate of the left edge of that layer. And the left-going amplitude was E sub I minus e to the minus I k zi, z minus zi. Let us now, in addition to these quantities, E sub I plus and E sub I minus, introduce two additional amplitudes. We'll denote them E sub I plus tilde and E sub I minus tilde, and those are defined as the values of the amplitudes with the phase accumulated over the thickness of the given layer. So E sub I plus tilde is equal to E sub I plus, and the phase shift e to the I kzi di. And same thing for the E sub I minus tilde. But now, obviously, the shift has an opposite sign. So what does it give us? Now, I got rid of the phase factors in the boundary conditions for the two interfaces as long as I use EI plus tilde and EI minus tilde in the left-hand sides instead of these products. So, in fact, what sits here is just the E sub 1 plus tilde and E sub 1 minus tilde. And same thing here. So I don't need to worry about the phase factors when I do the matching at the interface then, but I need to include the accumulated phases in the bulk of the layers. So in matrix form, I can write for the given layer E sub I plus tilde, E sub I minus tilde as a column vector is given by a diagonal transfer matrix. Simply those phase factors here. So here are the values without the tilde. And we can call this the T matrix for the ith layer. And then the boundary conditions at each interface can be written in the same way. These boundary conditions look the same as the ones we had for the first interface, except that now the quantities on the left have the tildes on top of them. We can now introduce a new simplified transfer matrix that connects E plus and E minus in layer I plus 1 with the amplitudes in layer I with a tilde. This is the explicit form of this matrix, as can be easily found by using the two boundary conditions. Overall then, we have this straightforward prescription for constructing the T matrix for the entire optical multilayer. For each interface, we have a T matrix that has this form, with the parameter kappa given by the ratio of the corresponding quantities for the two regions on the two sides of the interface. And in addition, for each bulk region, we have these phase factors represented in the form of a T matrix, and then the T matrix for the whole optical multilayer is given by a product of all these matrices. So from 0 to n, it will look like T tilde n minus 1, T n minus 1, that's the bulk matrix, then another interfacial matrix, n minus 1, n minus 2, T n minus 2, and so forth until we get to T 1, T 1, 0. That's the complete prescription. After the T matrix for the whole multilayer is found, the transmission and reflection coefficients can be found from these formulas, as we've seen previously. This completes our discussion of optical multilayers.